The engine ignition system provides the electrical spark required for initiation of engine combustion of the fuel-air mixture during start, auto relight, and when demanded by the cockpit crew, for example, when flying in inclement weather conditions. The system also performs engine flameout detection and automatic relight logic. The ignition system for each engine consists of 2 ignition exciters, 2 ignition leads, and 2 igniters. Note, for ground start only, 1 igniter is energized, and for each engine start, the ignition system alternates the igniters. The ignition exciters mounted on top of the compressor case provide a 14,000 to 18,000 volt DC output to the igniters. The igniter leads deliver high-voltage, low-energy electrical pulses from the ignition exciters to the igniters, where the 2 igniters provide the electrical sparks needed to start or maintain combustion. The igniter plugs consist of a center and outer electrode with a semiconductor surface coating at the tip between the 2 electrodes. The semiconductor material is used as a shunt to aid in ionizing the air gap between the 2 electrodes so that the plugs will fire. Engine ignition is controlled by the FADEC and integrated aircraft systems that automatically initiate ignition in response to engine core speed developed by the starter air system. Only 1 igniter is energized for ground starts so that latent faults can be detected. 2 igniters are energized for air starts, flameouts, loss of ARINC buses, a missed light-off, or if continuous ignition is requested by the pilot. During normal operation, electrical power for the ignition system is supplied by the aircraft AC system. On ground, with the APU running, the ignition exciters 1A and 2A are powered by the AC essential bus, while exciter 1B is powered by the AC bus 1, and exciter 2B by AC bus 2. In an electrical emergency condition, the igniters 1A and 2A have no interruption of power supply. In this case, the AC standby bus receives AC power from the inverter, DC-AC, which will be fed by the battery 1 via the hot bus 1. Selection of the ignition system can be performed manually from the flight deck by selecting the ignition switch to the off, auto, or override position, and automatically by the FADEC via aircraft systems. When ignition is selected manually, the command signal is sent directly to the FADEC. Each FADEC channel, regardless of in-control or standby status, can command both exciters and igniters on. Only 1 igniter is turned on for ground starts so that latent faults can be detected. 2 igniters are turned on for air starts, flameouts, loss of ARINC buses, a missed light-off, or if continuous ignition is requested by the pilot. The FADEC will turn the ignition off under the following conditions. On the ground, when the pilot commands ignition off by setting the ignition selector switch to off. Or in flight, when the pilot commands an engine shutdown by setting the start-stop selector switch to stop, and the pilot commands ignition off by setting the ignition selector switch to off. Ignition system indication is performed by icons displayed on the ICUS. Igniter A in green indicates that the FADEC has commanded igniter A to be energized due to a start on ground. Igniter B in green indicates that the FADEC has commanded igniter B to be energized due to a start on ground. Igniter AB in green indicates that the FADEC has commanded both igniters A and B to be energized due to a start in flight or an auto relight. Ignition off in cyan indicates that the FADEC has locked ignition off due to pilot procedure for dry motor cranking or if the fire handle has been actuated. In addition, Engine 1 no dispatch or Engine 2 no dispatch will be displayed on the CAS field in case igniter A has failed, while the A igniters on both engines are powered from the AC essential bus, so that in an electrical emergency condition, no engine in-flight start is possible. The control and power supply of the engine ignition is provided by an integrated engine and aircraft system that automatically initiates ignition in response to engine core speed developed by the starter air system. The MAUs interface with a three-position switch, off, auto, or override position, that allows the pilots to send ignition commands to the FADEC, which receives the ignition cockpit switch position from the MAUs and determines the required ignition command. Each FADEC channel, regardless of in-control or standby status, can command both exciters and igniters on. The local channel exciter is powered by the EICC for ignition exciter A and from the LICC for ignition exciter B when the local channel SPDA receives a relay driver signal from the FADEC. The cross-channel exciter is powered when the cross-channel SPDA receives an ignition on signal from the local channel SPDA via the ASCB bus. Only one igniter is turned on, using the relay driver signal for ground starts so latent faults can be detected. Two igniters are turned on for air starts, flameouts, loss of ARINC buses, a missed light off, or if continuous ignition is requested by the pilot. The engine air system conducts air from and through the engine for aircraft pneumatic and anti-icing system use, engine compressor control, nacelle sealing, and engine cooling purposes. The air system includes the compressor control system, the nacelle sealing, and the engine compartment cooling. The engine buildup unit air management system basically comprises three major ducts. One delivering airflow coming from the compressor fifth stage, called the LP, low pressure line, and one coming from compressor ninth stage, called the HP, high pressure line. These two ducts form a combined manifold that is connected to the pylon. Engine cooling includes both internal and external cooling. Engine external cooling consists of both the fan and core compartments cooling. In addition, dedicated plumbing is provided for FADEC internal cooling requirements. Two NACA scoops that are located on the upper surface of the inlet outer barrel provide fan compartment cooling. During flight, air enters the scoop and is directed to the appropriate region in the fan compartment. The air is then discharged overboard through vents located in the lower region of the fan compartment. The core compartment is cooled with fan air. Cooling air enters core compartment through holes located near the inner cowl support ring. Fan air flows through the core compartment and is discharged back into the flow at the aft vent. Engine internal cooling is primarily performed by high-pressure compressor air. The high-pressure stator segment vanes and platforms are cooled by compressor discharge air. The discharge air enters through inserts in the inner and outer platforms of the vanes and exits through holes in the leading and trailing edges of the vanes to form a film cooling surface for the vanes. The HPT rotor blades are top-coated with a thermal barrier coating, a white ceramic, to lower the metal temperature and improve part life. The blade root has an entry hole that receives the compressor discharge air and exits the blade through holes in the blade leading edge, trailing edge, and tip areas to form a film cooling barrier for the blade. The Stage 1 low-pressure turbine nozzle is cooled using high-pressure compressor fourth-stage bleed air. The Stage 1 LPT nozzle also provides a conduit for delivering cooling air to the high-pressure turbine aft rotor cavity and for LPT rotor cooling. All other low-pressure turbine airfoils, stages 2 through 4 nozzles, and stages 1 through 4 blades, are uncooled. The compressor control is used to control the flow of air through the engine and to maintain the compressor and booster operability margins. The compressor control system comprises the variable stator vane, VSV, variable bleed valve, VBV, and the transient bleed valve, TBV. The variable stator vane, VSV, actuation system varies the angle of attack of the variable compressor stator vanes to maintain a smooth, turbulence-free airflow through the compressor rotor at all engine operating speeds, temperatures, and altitudes by means of two VSV actuators that are mounted on two sides of the forward compressor stator case. The FADEC continuously determines the needed VSV position based on engine sensor inputs and sends, when required, an electrical signal to the FMU, which sends servo fuel to both VSV actuators. Movement of the actuators will adjust the compressor stator vanes to the required position via torsion tubes, links, and actuating rings. Each of the two actuators contains a single LVDT. One actuator provides stator vane position feedback to the in-control FADEC channel, while the other actuator provides position feedback to the standby channel. The variable bypass valve system controls the booster operating limits, provides optimum booster performance at steady-state conditions, and prevents stall. The system consists of two VBV actuators which operate via adjustable links, bell cranks and actuating rings, 10 VBV doors that open to bleed excess booster discharge airflow or close to allow zero bleed. The VBV system is controlled by the FADEC and operates from idle, doors open, to takeoff power, doors closed. During reverse thrust, the FADEC will partially open the VBV doors to increase booster stability and to prevent core engine foreign object damage. During engine shutdown, the VBV doors are driven open. The FADEC determines the required VBV position based on engine sensor inputs and sends an electrical signal to the FMU, which supplies servo fuel to both VBV actuators. Movement of the actuators will open or close the 10 VBV doors. Each of the two actuators contains a single LVDT. One actuator provides bleed valve position feedback to the in-control FADEC channel, while the other actuator provides position feedback to the standby channel. The transient bleed valve, TBV, system bleeds air from the compressor rotor to provide compressor stall margin. Using aircraft and sensor inputs, the FADEC uses fuel metering valve servo fuel to open the transient bleed valve during engine starts and during engine transients to protect the engine stall margin. When the transient bleed valve is commanded open, compressor discharge air is exhausted overboard into the exhaust nozzle. Dual LVDTs attached to the valve provide position feedback to each FADEC channel. The engine control system is a computer-based electronic engine control system comprised of a two-channel, full authority digital electronic control, FADEC. A fuel metering unit, FMU. A permanent magnet alternator, PMA. Engine sensors. Compressor and turbine control valves and actuators. An ignition system for each engine, a thrust control quadrant, engine cockpit switches, ignition and start-stop switches, MAUs, MCDUs, SPDAs, and ICCs. The system controls the engine in response to thrust command inputs from the aircraft and provides information to the aircraft for cockpit indication, maintenance reporting, and engine condition monitoring. The engine thrust control is provided by the thrust management system within the FADEC and controls the engine in response to thrust command inputs from the aircraft. The aircraft provides 28-volt DC to each FADEC channel for system power when the engine is not running or when performing a FADEC-controlled engine start with an engine speed below 50% N2. 28-volt DC for T2 sensor anti-icing, and 115-volt 400 Hz power to each ignition exciter. Selection between the aircraft 28-volt DC and the PMA power is performed automatically by the FADEC when the engine speed is greater than 50% N2. The engine monitoring function is also performed by the FADEC by monitoring inputs from various sources and by performing tests for failures and over-limit conditions. The FADEC supplies ARINC 429 outputs of engine parameters and status to other aircraft avionics and supplies information to aid in detection, reporting and storing of faults, engine dispatch level and exceedance information, and data for trend data records. The FADEC will perform diagnostics on its input data to determine if any failures exist. If a failure exists, and if the failure is one that the pilot should be aware of, a message or indication will be displayed. The Central Maintenance Computer, CMC, will log the fault message for display when accessed by maintenance personnel. The CMC will try to correlate the ICAS messages with FADEC fault messages so that the maintenance crew can use the CMC troubleshooting manual to interpret fault indications from the FADEC and determine the appropriate line removable unit, LRU, that has failed. A limited number of faults will be stored in the FADEC non-volatile memory, but this data is only available by directly accessing the FADEC using portable test equipment. The Thrust Control Quadrant, TCQ, is located on the aircraft cockpit center console and combines two lever assemblies, one for each engine, which may be operated independently, in unison, or in auto throttle mode. The Thrust Control Quadrant, TCQ, contains the following main components: the thrust control levers, the thrust control quadrant case, the thrust lever angle dual-channel RVDTs, which provide lever position signals to the FADECs, the electrical idle stop solenoid, the aircraft system's micro switches set, 6 per lever, the takeoff go-around switches, the auto-throttle disconnect switches, and the auto-throttle servo system. The thrust lever is equipped with a mechanical trigger assembly, which is used to enable movement of the thrust lever past a detente position to the thrust reverse range. The full travel of the thrust levers is 82.0 degrees, divided into 5 settings, which provides RVDT's output signal corresponding to max reverse at 0.5 degrees TLA, minimum reverse at 12.0 TLA, idle at 22.0 TLA, takeoff go-around at 75.0 degrees TLA, and max power at 82.0 TLA. These 5 settings are also identified and illuminated on both sides of the thrust control quadrant. The thrust control quadrant case is provided with 2 soft detents, grooves, one at takeoff go-around, 75.0, and the other at minimum reverse, 12.0. The max reverse position is achieved by pulling the thrust lever against a spring. Positive adjustable stops are provided at the max and max reverse positions to limit the movement of the thrust levers. Thrust levers are capable of unrestricted forward movement from idle to max power. Two electrical idle stop solenoids, one for each thrust lever, are installed on the thrust control quadrant at the 22.0 degree TLA position. These solenoids provide protection against thrust lever command below idle in flight. Power to these solenoids is provided by the SPDA and allows selection of reverser thrust immediately after touchdown and during ground operations. Position indication is provided by 2 microswitches, one for each solenoid, which sense the idle lock shafts and trigger messages on the ICAs whenever the solenoids become unlocked during flight or locked on ground. Each thrust lever incorporates an independent and isolated RVDT containing 2 electrically independent channels, which are direct wired through segregated TCQ interface connectors to the FADEC channels of its engine. The thrust control quadrant provides a set of 6 microswitches per lever. These switches are designed to automatically provide electrical signals to several aircraft systems as a function of the thrust lever angle. Each switch pole is adjusted at a specific thrust lever angle as required for the respective system control, such as the thrust reverser system and the auto brake system. The takeoff go-around switches are mounted on each thrust lever to enable the pilot to manually generate a takeoff go-around signal. They are momentary push-button, single-pole, single-throw. The AT disconnect switches on each thrust lever enable the pilots to manually switch off the auto throttle system. The auto-throttled servo drive with associated control electronics is provided for each lever. The servo drive features a motor and gearhead combination to provide required force to operate each lever. The auto-throttle system controls the servos via the control electronics. The system consists of 2 motor controller units, MCU, and 1 signal control unit, SCU, which transmits via RINC 429. A slip clutch between thrust levers and servo drive allows pilots to reposition thrust levers without shutting off AT function. The levers return to the last AT position when pilot effect is removed. During a manual, hands-on operation of the thrust levers, the MCU is inactive, disabled. The pilot movement of the thrust levers is transformed via the anti-backlash gears into an RVDT rotation. The RVDT position determines the engine thrust setting via the FADEC. A slip clutch is placed between the thrust lever and the servo drive to allow the lever operation without backdriving the servo motors. In the auto-throttle mode, the MCU is enabled, and its action is controlled by the AT system, located inside the MAU via the SCU. The MCU requires two valid signals to operate: the enable signal and the velocity with direction signal. As long as these two valid signals are available, the MCU seeks to achieve the commanded speed by closing the loop on the motor Hall effect sensor. The motor speed is transmitted to the AT system, MAU, via the SCU. The emergency shutdown subsystem provides a way of controlling the flow of fluids and air to and from the engine during emergency procedures. In an emergency situation, the pilot can stop the engine immediately by pulling the fire handle. This action stops the fuel flow to the engine and also stops the flow of the hydraulic fluids and pneumatic air from the engine to the aircraft systems. Pulling the related fire handle will stop the engine in an emergency situation. The fuel shutoff valve will close the valve, which stops the fuel supply to the engine. The hydraulic system shutoff will also close, isolating the engine side of the hydraulic system from the airframe hydraulic system. The handle also generates a signal which is sent via the MAU to the air management system, which closes the high-pressure shutoff valve and the engine bleed valve. This isolates the engine air system from the airframe systems. In the following interaction, you can select and close the valves. Carefully observe the effect the valve closing has on the system. The N1 is a primary engine instrument and is displayed to the crew as a dial, pointer, and digital readout for each engine. The N1 digital readout is a numerical display of the fan rotor speed, displayed as a percentage of total RPM for each engine. The N1 digital readout is displayed whenever N1 information is valid. The N1 dial provides a graphical representation of the current N1. The N1 for each engine is indicated by a rotating analog pointer. The dials display pie-shaped shading in the area between the 0% position of the scale to the current pointer position. There are two arc segments that make up the N1 dial. Segment 1, 0% to N1 red line, represents the normal range of N1. And segment 2, red line and all positions higher, is the red range of N1. In the event of a loss of N1 signal, N1 pointer is removed from the display. The red line is the exceedance threshold and represents the maximum allowable N1 value. The N1 reference arc displays the difference between the actual N1 value and the requested N1 value applied by the thrust lever position. The N1 wing anti-ice WAI bug is displayed on the outside of the N1 dial. The in-1 wing anti-ice bug indicates the minimum in-1 value when the wing anti-ice is on and the aircraft is on the final approach phase. The thrust rating enunciation is displayed as text in the center above the in-1 dials. Selected thrust rating is provided by the thrust rating selector, TRS, and is based on phase of flight. A flex takeoff is used to reduce the engine thrust, to account for favorable takeoff conditions. An in-1 rating bug is displayed at the corresponding in-1 value on the dial. Takeoff thrust ratings are selected via the MCDU on the Takeoff Dataset menu page. The flex temperature limits thrust to a value less than the active takeoff rating if the flex takeoff option is selected on and a flex temperature is set to a value greater than the takeoff temperature, pilot inputs. Flex temperature is displayed between the in-1 dials below the ATTCS status enunciation. Flex temperature is selected via the MCDU on the Takeoff Dataset menu page. The max thrust is the maximum allowable in-1 value that can be selected moving thrust levers to the max position. Max thrust is displayed for each engine as a tick mark on the in-1 dial. The maximum in-1 value will always be lower than the in-1 red line. When ATTCS is enabled or armed, it is enunciated with the label ATTCS above the in-1 dials. If ATTCS is active, in case of an engine failure, the ATTCS enunciation is removed from the display and TO1 RSV, TO2 RSV, TO3 RSV, or GA RSV are shown. When an engine is shut down by crew action, the engine shutdown enunciation off is displayed in the center of the in-1 dial for the affected engine. When an engine flames out or is shut down without crew action, the engine shutdown enunciation fail is displayed in the center of the in-1 dial for the affected engine, and a caution CAS message is displayed. The thrust reverser enunciations are displayed under the in-1 dials whenever the thrust reverser is not stowed. This is shown with the enunciation REV. An amber REV enunciation if the thrust reverser is transitioning from one state to another, stowed to or from deployed. The enunciation is displayed in red inverse video in case of an inadvertent deployment in the air, and a CAS message will be displayed. The ITT is a primary engine instrument and is displayed to the crew as a dial, pointer, and digital readout for each engine. The ITT readout is a numerical display of the inter-turbine temperature for each engine, displayed in degrees Celsius. The ITT dial provides a graphical representation of the current inter-turbine temperature. ITT for each engine is indicated by a rotating analog pointer. The dials display pie-shaped shading in the area between the beginning of the scale to the current pointer position. The ITT red line represents the maximum ITT for the certified thrust rating modes. The lengths of the arc segments on the ITT dial and the location of the red line tick mark vary depending on the red line data provided by the FADEC. The ITT amber line is the limit that corresponds to the maximum continuous ITT limit. The ITT amber line is displayed on the ICUS only in flight after the end of the takeoff phase. The engine fire enunciation indicates detection of an engine fire condition for the engine. The igniter enunciations indicate the various states of the igniters for each engine. The label A and or B or off enunciations are displayed under the IGN label. The possible enunciations are IGN A indicates igniter A has been commanded on. IGN B indicates igniter B has been commanded on. IGN A B indicates igniters A and B have been commanded on. IGN off indicates igniter locked off. The N2 is displayed as a digital readout for both engines. If the N2 value is invalid or outside of the displayable range, the N2 digital readout is replaced with 3 dashes. For each engine, the WML enunciation is displayed when conditions of an engine flameout is detected and the engine has not been returned to its running condition. The fuel display consists of digital readouts for left and right fuel flow, left and right fuel tank quantities, and total fuel quantity. The units for fuel are pounds or kilograms as determined by aircraft configuration. This is not crew selectable. The fuel flow in kilograms or pounds per hour is displayed for both engines as digital readouts directly under the N2 display. If the fuel flow data is invalid or outside of the displayable range, the readout is replaced with 3 dashes. The Integrated Engine Vibration Monitoring System indication on the ICUS consists of one indicator for each engine and is divided into an LP and an HP scale. The LP indicator represents the N1 rotor and the HP indicator represents N2 rotor. The indication will be shown in green from 0 to 3.9 and in amber from 4 to 5. In case the integrated engine vibration monitoring values are higher than 5, the maintenance computer and flight data recorder will be able to continue recording vibration levels up to 10 units. The Integrated Engine Vibration Monitoring System, IEVM, monitors vibrations from the N1 and the N2 rotors by accelerometers mounted on the engine by extracting 1 per revolution vibration levels. The speed signals driving the center frequency of the tracking filters are provided by the speed pickups N1 and N2. Once per revolution signal is also processed in order to compute LP rotor engine imbalance, phase and displacement. Vibration levels are transmitted to the cockpit for engine vibration indication. The Integrated Engine Vibration Monitoring System consists of 2 transducers per engine. One is fitted on the fan front frame, and the second is fitted on the HP turbine flange. The 2 transducers allow the possibility of 2-plane trim balancing in order to reduce the cabin noise. For each transducer, its signal is compared with dedicated N1 and N2 speed signals to determine the tracked LP and HP vibration levels. This gives a total of 4 vibration values. LP tracked vibration at the front frame bearing case. LP tracked vibration at the HP turbine flange. HP tracked vibration at the front frame bearing case. HP tracked vibration at the HP turbine flange. The system permanently monitors the engine when running and sends its signals to the cockpit. In case the IEVM values are higher than 5 units, the maintenance computer and flight data recorder will be able to continue recording vibration levels up to 10 units. The exhaust system of the engine discharges the primary and bypass air from the propulsion system. The exhaust system includes the nozzle and the thrust reverser system. Primary air is the air that enters the engine near the fan blade platform, continues through the low-pressure axial booster, the high-pressure compressor, the combustor, the high and low-pressure turbines, and then is accelerated and exhausted to atmosphere through the primary nozzle. The inner wall of the primary nozzle and the outer wall of the center body form the primary nozzle flow path. The bypass air, discharged from the outer portion of the fan, is approximately 4/5 of the total airflow, bypasses the core engine, and flows through the thrust reverser to atmosphere. In the forward thrust mode, this bypass air is accelerated and exhausted aft to atmosphere by the fan nozzle, which is the duct of the thrust reverser, formed by the inner wall of the thrust reverser's translating cowl and the outer surface of the inner fixed structure. In the reverse thrust mode, the transcowls are deployed aft to block the fan nozzle. The fan air is then directed radially outward through the cascades exposed by the translating cowl, which directs the fan air toward the front of the engine. The primary exhaust nozzle consists of a conical nozzle and a center body, which both provide the necessary core engine exhaust area. The nozzle trailing edge is scalloped to assist in mixing the fan and core flows, which helps to reduce exhaust noise. The thrust reverser assembly forms the fan airstream exhaust nozzle when stowed, and reverses the direction of the fan airstream when deployed. It has two halves that are hinged to the aircraft pylon at the top, and latched together at the bottom to permit opening the thrust reverser for engine access or removal. Both the fixed structure and the transcowl halves are latched together. Each thrust reverser half forms the inner and outer surfaces that direct the fan airstream and contains the translating cowl cascades, actuators, and necessary structural components. When deploying, the translating cowl is driven aft, blocking the fan air passage and exposing the cascades that direct the fan airstream outward and forward. The primary exhaust system provides a fixed area annulus for exhausting the core engine gas stream flow, and provides a continuation of the aerodynamic cowling from the aft core cowl interface. It consists of a primary nozzle, which attaches to the turbine frame outer flange, and a center body, which attaches to the turbine frame hub flange. The primary exhaust nozzle assembly contains a forward flange for attachment to the engine turbine frame outer flange, and a conical section sheet metal skin welded to the forward flange. A fire shield is also incorporated into the nozzle assembly at the 12 o'clock position. The nozzle has a chevron design which helps to reduce the engine core noise levels. In order to ensure pylon sealing, no chevrons are located at the 12 o'clock position. The primary exhaust nozzle's center body contains a forward flange for attachment to the engine turbine frame hub flange, and a formed sheet metal conical section with internal stiffeners joined to the forward flange. The aft end of the center body is open to exhaust the core compartment ventilation air to atmosphere. The thrust reverser assembly is located directly aft of and is clamped to the aft fan case. It forms a duct for fan exhaust air when the left and right assemblies are latched in place. Each thrust reverser half consists of a fixed structure that supports the transcowl, houses the cascades, and contains the thrust reverser actuation system. In the forward thrust configuration, the transcowl is in the forward stowed position covering the cascades. In the reverse thrust configuration, the transcowl is in the aft deployed position blocking the fan duct and exposing the cascades. Each transcowl is attached to its fixed structure half by an upper and a lower rail and the actuators, and is connected together by a set of two latches at the 6 o'clock position. The thrust reverser system is used to deflect and redirect the fan airstream so as to create a reverse thrust component. The thrust reverser set is composed of left and right-hand assemblies latched together at the 6 o'clock position that form the fan exhaust nozzle for forward thrust operation. The assemblies have a translating cowl that moves aft when commanded by the thrust lever, resulting in a redirection of the fan airstream during reverse thrust operation. Each thrust reverser half is operated by two hydraulic actuators pressurized by the aircraft hydraulic system. The actuators extend when reverse is selected and drive the transcowl aft along tracks on the upper and lower beams of the thrust reverser fixed structure. Appropriate interlocks and position sensors, which indicate the position of the transcowl to the flight crew, are incorporated in the system. The thrust reverser actuation system positions the translating cowls of the thrust reverser in response to commands from the Full Authority Digital Electronic Control, FADEC, and Aircraft Electrical Circuit. The thrust reverser actuation system, TRAS, is a synchronized linear hydraulic actuation system that utilizes the aircraft hydraulic supply to deploy and stow the translating cowl during engine reverse thrust operation. The thrust reverser actuation system has two operational positions: cowls stowed and locked, forward thrust position, and cowls deployed, reverse thrust position. The thrust reverser actuation system consists of the following major components: two synchronized locking actuators, two synchronized non-locking feedback actuators, one isolation control unit, ICU, one directional control unit, DCU, one electro-hydraulic cowl lock, one set of three synchronizing cables, the manual drive assembly, and the flex tube assembly. Each thrust reverser translating cowl has two actuators, one SLA and one SFA, to move the cowl between the deployed and stowed positions. A flexible sync shaft runs between the actuators to synchronize the actuator movements. One actuator on each thrust reverser half is equipped with a lock mechanism, while the other actuator has a position feedback sensor, LVDT, that provides the position of the transcowl to the FADEC. One isolation control unit and one direction control unit control all four actuators. The isolation control unit isolates the thrust reverser system from the aircraft hydraulic supply, while the direction control unit provides hydraulic control of the actuators and cowl lock. The thrust reverser is controlled from the cockpit through a thrust reverser control integrated into the thrust control quadrant, TCQ. The TCQ allows the thrust reverser to be deployed or stowed by hydraulic actuators mounted in the thrust reverser. The FADEC receives various inputs such as weight on wheels, wheel speed, and thrust lever angle from the aircraft systems, and activates the ground relays when all signals are correct for reverse thrust. Once the thrust lever is retarded into the reverse range of the quadrant, the cowl lock and DCU are energized, which enables the thrust reverser to be deployed. The ICU contains an isolation valve, which is normally held in closed position by a spring and by return pressure. The isolation valve is moved by the normally closed simplex solenoid valve, which then directs pressurized oil to the pilot area of the spool, positioning the valve so that pressurized oil is allowed into the rest of the system. For engine maintenance, the valve may be locked in the closed position by an inhibit lever. The lever positions a stop for the valve and may be locked in both states by a pip pin. The direction control valve has two positions, stow and deploy. The valve is normally held in the stow position by a spring and by return pressure. The DCU incorporates a normally closed single-coil solenoid valve. When energized, the solenoid valve allows pressure to the cowl lock circuit, which disengages the cowl lock and provides a pressure signal to the direction valve so that it moves to the deploy position. The two translating cowls are actuated by two synchronized locking actuators and two synchronized feedback actuators. All four actuators are synchronized by three flexible shafts located inside two sync tubes and one flex tube. The synchronized locking actuator, SLA, has an internal lock mechanism that can be released by a manual unlock handle. The synchronized feedback actuator, SFA, has no internal lock but is in design and construction similar to the locking actuator. The SFA has a feedback mechanism consisting of a linear voltage displacement transformer, LVDT, actuated by a rod attached to the lead screw, which provides the indication of the actuator extension. When the thrust reverser system is in the de-energized state, the actuators are at rest in the flush, stowed position. All electrical signals are removed and all locks are engaged. Clearance in the cowl lock ensures it is unloaded during normal operation. The ICU isolates the hydraulic supply so that all system components are at return pressure. The thrust reverser deploy sequence has two distinct phases, overstow and extend. When the thrust lever is selected to the reverse position, simultaneous electrical signals are sent to release the electro-hydraulic cowl lock solenoid and to operate the ICU and DCU solenoid valves. Movement of the isolation solenoid valve initiates three actions. Pressure is directed to the DCU. Pressure is directed to the retract area of all actuators. And a pressure on signal is generated by the ICU pressure switch. When pressure is applied to the rod ends of the actuators, they retract to the overstow position where the cowl lock and actuator internal locks may be released. The DCU solenoid valve directs fluid to the cowl lock circuit. As pressure increases, the electro-hydraulic cowl lock releases and allows pressure to the DCU control valve spool. Movement of the DCU control valve permits oil pressure to the extended areas of the actuators. As pressure increases in the actuator head chambers, the actuator internal locks are released, and pressure then moves the translating cowls to their full deployment. The nut attached to the hydraulic piston causes the internal lead screw to rotate, which in turn drives the worm wheel in the actuator head. The worm wheel in each actuator is connected to its neighbor via flexible cables running within the extend hydraulic pipes. The efficiencies of the screw, worm gears, and shafts act to retard a leading actuator. In this way, all actuators are restrained to move in unison. After a period of time, the ICU solenoid is de-energized and the spool valve is closed. The pressure switch indicates that the pressure has been removed and the direction control valve returns to the stow position. The actuators are held in the deploy position by the air loads, and the cowl lock returns to the locked position, waiting to ratchet the cowl lock as it restows. To stow the cowls, the DCU and electrohydraulic cowl lock solenoids are de-energized. After a time delay, the ICU solenoid is energized. The control valve moves into the stow direction by hydraulic pressure and assisted by spring pressure, allowing hydraulic pressure to the stow side of the actuators, allowing deployed hydraulic pressure to return. The cowl lock circuit depressurizes, and the electrohydraulic cowl lock returns to the locked state, automatically re-engaging as the cowls are retracted to the stowed position. After the thrust reverser is stowed, the ICU solenoid is then de-energized, which returns the system to the de-energized state. The thrust reverser is electrically controlled by the FADEC and protects the thrust reverser actuation system against inadvertent thrust reverser deployment and inadvertent thrust reverser stow. The FADEC thrust reverser interlock function is implemented with 2 single-contact ground relays per FADEC channel. One ground relay interrupts power to the hydraulic power functions, and the other interrupts power to the direction and locking functions. For the control function, each FADEC channel receives hardwired LVDT position inputs and hardwired lock switch discrete inputs from the thrust reverser actuation system. To deploy the thrust reversers, the pilot commands thrust reverser deployment by lifting the idle stop trigger on the thrust lever and moving the lever into the reverse quadrant. The idle stop trigger can only be lifted when the idle stop solenoid is energized by using the SPDA. Logic to energize this solenoid requires, for example, a weight on wheel signal. The thrust lever RVDT is read by the FADEC. And once the conditions for enabled are met, the FADEC energizes the ground relays, which in turn energize the solenoids for the ICU and DCU cowl locks. When the thrust lever is pushed to forward idle or above, thrust reverser stow is initiated. The DCU and cowl lock solenoids are de-energized, and after a time delay, the ICU solenoid is energized by the FADEC, which also initiated the DCU and thrust reverser stow sequences. Once the thrust reverser actuation system LVDT signal indicates less than 10% deployment, the FADEC will declare that the thrust reverser is stowed and de-energizes the ICU solenoid. The purpose of the engine oil system is to provide lubrication and cooling to the turbine engine main shaft bearings and the accessory gearbox bearings. The engine oil system can be divided into the following subsystems: the oil pressure system, the oil scavenge system, the oil vent and sealing system, and the oil indication system. Each engine has an independent lubrication supply system, which contains an engine-driven positive displacement vane-type pump to supply oil to the various engine components requiring cooling and lubrication. There are two sumps in the engine that require lubrication. First, the forward sump, which holds the number 1 and number 2 low-pressure fan rotor bearings, the power takeoff, and the number 3 ball and the number 3 roller bearings. Labyrinth seals, pressurized with booster discharge air, seal the forward sump at each end. And the aft sump holds the number 4 and the number 5 bearings and is also sealed with booster discharge air. The engine lubrication system contains the following main components: an oil tank, a combined oil level sensor and oil temperature sensor, the fuel oil cooler, the servo fuel oil heat exchanger, the lube and scavenge pump, the electrical chip detector, the oil filtration module, the oil filter impending bypass sensor, the oil pressure transmitter, the low oil pressure switch, and the oil service panel. The oil tank is a cast housing and is mounted on the fan case at the 3 o'clock position. It includes a gravity fill port with filler cap, a sight glass for visual oil level indication, a drain plug, and an oil level temperature sensor. The oil tank total capacity is 16.7 liters, 17.6 U.S. quarts, an expansion area of 1.9 liters, 2 U.S. quarts, and a usable oil capacity of 9.5 liters, 10 U.S. quarts. All lubrication oil must pass through a disposable filter contained in the filter module. The module incorporates both a filter bypass valve to limit excessively high filter differential pressure and a cold start relief valve to bypass high viscosity oil in a low temperature condition. The filter impending bypass switch monitors the differential pressure between the lubrication filter inlet and the lubrication filter discharge. It provides a discrete electrical output to the aircraft MAU when the filter is contaminated. The MAU sends a signal to the ICUS to alert the flight crew. The servo fuel oil heat exchanger is located on the fan case aft of the oil tank. The servo fuel oil heat exchanger uses heat from the engine lubrication oil to increase the temperature of the fuel before it goes to the servo elements in the fuel metering unit to prevent ice in the servo system. The main fuel oil heat exchanger is located on the fan case at 2 o'clock just above the oil tank. It decreases the temperature of the engine oil and increases the temperature of the FMU fuel. The lube and scavenge pump is a rotary vane type pump. The pump shaft is driven by the accessory gearbox and provides oil flow at any time the core engine is turning. The lube and scavenge pump delivers oil under pressure to the engine bearings and gears and then recovers the oil for reuse. The electrical chip detector is designed to trap magnetic particles that are suspended in the scavenge oil. This is accomplished with the use of a permanent magnet immersed in the scavenge oil flowing from the lube scavenge pump, returning to the oil reservoir. A screen installed in the detector collects non-magnetic debris for inspection and identification. A self-closing valve seals the scavenge return line to prevent oil drainage when the chip detector is removed. The combined oil quantity transmitter and RTD-type oil temperature sensor is mounted on top of the oil reservoir and provides indication of the oil level on the MFD status page and the oil temperature within the oil tank to the ICUS. In order to indicate the oil level, the transmitter incorporates a number of reed switches. As magnets mounted to a float assembly move up or down past a series of switches, the reed switches close, inducting an electrical voltage through separated resistors of each switch. The total resistance, as a voltage divider signal from each of the individual circuits, is then displayed on the MFD. The low oil pressure switch is located on the aft side of the AGB and provides a signal to the aircraft warning systems when oil pressure is low. The operation of the low oil pressure switch at engine startup is as follows. When oil pressures are low, the switch circuit will send a signal to the aircraft indicating low pressure. As oil pressure increases, the switch's contacts open and the signal to the cockpit is no longer applied. Should oil pressure decrease due to a malfunction, the switch contacts will close and again send a signal to the cockpit. The oil pressure transmitter located on the oil filter module assembly provides an electrical signal equivalent to the differential pressure of the oil supply pressure at the filter exit and the AGB. This pressure differential is converted to an electrical signal that is sent to the ICUS. The engine oil flow begins when the engine is started. Oil from the tank enters the supply element of the main lubrication and scavenge pump. From this pressure element, the oil passes through the filter module where the oil is filtered. From the oil filter, the oil flows to the Servo fuel oil heat exchanger and main fuel oil heat exchangers that cool the oil. After leaving the heat exchangers, the oil flow divides into several circuits that lubricate the front and aft sumps, the AGB, and the transfer gearbox. Oil is returned to the oil tank by 4 scavenge pump elements in the main lubrication and scavenge pump, with 1 element each for the AGB climb, AGB dive, forward sump, and aft sumps to scavenge oil and return the oil to the oil tank. The combined scavenge oil is routed past a master electrical chip detector and then into the oil tank de-aerator and tank main compartment. The engine oil system can be monitored on the ICUS and MFD status page. The ICUS indicates the engine oil pressure and the oil temperature. The engine oil pressure readout is displayed in pounds per square inch for each engine. Indication is green in normal operation, amber when operating in the cautionary range, and red when operating limits are exceeded. The engine oil temperature readout is in degrees Celsius for each engine. Indication is green in normal operation and amber when operating in the cautionary range. Engine oil level status is displayed on the MFD status page in quarts. Each engine has its own scale with pointer and a numerical display. The left scale corresponds to engine 1 and the right scale is for engine 2. The scale is divided into 2 segments. The bottom segment is the amber region and an upper segment, which is displayed in white, is the normal region. The engine starting system is designed to provide sufficient rotor speed to initiate combustion light-off and to obtain self-sustaining engine propulsion. The starting system includes an air turbine starter, ATS, a starter control valve, SCV, portions of the bleed air system, and starting control panel. Engine starting is a combined aircraft and FADEC operation. The FADEC controls fuel flow, the starter command, and the ignition command, while the aircraft controls the starter control valve and the engine-driven pump, EDP, of the hydraulic system, and also switches power to the ignition exciters as commanded by the FADEC. The aircraft also manages the bleed system interface during starts. There are two different methods by which the engine can be started: by means of an assisted air turbine starter start or an unassisted windmill start. For an assisted start, the pneumatic system has to be configured to provide air to the starter control valve inlet. By selecting the start switch on the power plant control panel momentarily to the start position, pressurized air is directed to the air turbine starter, which rotates the engine rotor via the AGB. The FADEC automatically commands the ignition on and fuel flow. The FADEC schedules the fuel flow to accelerate the engine to idle, de-energizes the starter control valve at approximately 50% N2, and turns the ignition off when the engine reaches idle. Note that the isolation valve is automatically controlled only if the cross-bleed switch is selected to auto. For the unassisted start, the engine rotors are rotated by the aircraft toward airspeed, providing windmilling rotation. The start is commanded through the start switch, and the FADEC then automatically commands ignition and fuel. Ignition will be turned off when idle speed is reached. Note, the hydraulic engine-driven pump, EDP, is unloaded by energizing the EDP solenoid during engine windmill starts in order to reduce drag on the core rotor. The starter is a single-stage air turbine starter, clamped to the AGB aft face adapter pad by a V-coupling clamp. The air turbine starter converts a pressurized air supply into the driving torque required to rotate the engine into spool. It also provides motoring during maintenance practices or for engine cooldown. When the FADEC signals the starter control valve to open, airflow passes through the starter turbine and the starter output shaft rotates, which turns the accessory gearbox drivetrain and rotates the core engine. The air turbine starter consists of an axial turbine, reduction gearing, engage-disengage mechanism, and a splined drive shaft to mate with the engine. The starter bearings, gears, and splines are lubricated by a self-contained lubrication system within the starter. The air supply, which is controlled by the starter control valve, drives the axial turbine in the starter. The torque provided by the turbine is transmitted through a planetary reduction gear set and an overrunning clutch to a splined output shaft, which mates with the accessory gearbox. When starter cutout speed is reached, the starter control valve will be commanded closed, shutting off the air supply to the starter. With the air supply shut off, the turbine will no longer have the energy to sustain torque and will slow down. The Sprague-type overrunning clutch automatically disconnects the turbine and planetary gear set from the output shaft, allowing them to stop while the output shaft continues to turn with the engine. The starter control valve, SCV, is a spring-loaded, closed, pneumatically actuated, electrically controlled, butterfly-type shutoff valve with an open position indication switch. The solenoid is a pull type and operates with 28-volt DC aircraft power. The valve incorporates a visual position indicator and a manual override socket drive to open the valve in case of physical or electrical failure. The starter control valve is controlled by the FADEC using an aircraft-powered 28-volt DC solenoid. The two-position valve is normally torsion spring-loaded and air pressure closed. To open the SCV, the FADEC energizes the solenoid, closing off pressurized air from chamber B. Since chambers B and C are now connected to ambient, this allows the duct pressure in chamber A to move the piston in a linear direction towards the valve open position. This linear movement is transferred by a rod assembly to the valve shaft, creating a rotary movement which opens the butterfly valve. After the start sequence is completed, the FADEC de-energizes the SCV solenoid. Duct air pressure assisted by torsion spring pressure now acts on the piston to move the piston in a linear direction towards the closed position. This linear movement is transferred into a rotary movement, which closes the butterfly valve. The start and stop sequence is initiated by the Stop Run Start selector switch on the power plant control panel. The stop position is used to shut down the engine or to stop dry motoring. By moving the switch momentarily to start and releasing it back to run, the automatic engine start sequence is initiated. Or if the ignition switch is selected to off, motoring can be commanded. Do not keep the switch in the start position for more than 3 seconds, or the FADEC will stop the start sequence and shut down the engine. An assisted start sequence is carried out as follows. The ignition switch is placed in auto position. The bleed air system is then configured so that air at the SCV is available. The start-stop selector switch is momentarily selected to start, so that the MAU senses the start switch closure and sends the start switch signal to the FADEC via the RINC. If the proper conditions are met, the FADEC sends the Energize Starter command signal via RINC to the MAU, which passes the signal on to the SPDA. Which energizes the starter control valve solenoid. The starter control valve opens, which closes the starter SOV feedback switch. The switch position is sensed by the MAU and transmitted to the FADEC via RINC. The FADEC commands the ignition on at approximately 9.5% N2. And the fuel metering valve to open at 19.1% N2. For in-flight starts, the FADEC will open the metering valve when N2 is greater than 19.1%, or after 15 seconds when N2 is not reached 19.1%. The FADEC will schedule the fuel flow to accelerate the engine to idle and will de-energize the SCV at approximately 50% N2. Ignition will be turned off when the engine reaches idle. Note, the maximum allowable internal turbine temperature for engine start is 815 degrees Celsius. The unassisted or windmilling start is performed according to the following sequence. The ignition switch is set to auto, and the pneumatic system is configured so that no air is available at the SCV. The start-stop selector switch is momentarily set to start. The switch position is sensed by the MAU, which sends the start switch signal to the FADEC via RINC. The FADEC latches the start command and sends the Energizer start command via the MAU to the SPDA, that energizes the starter control valve. Since no pneumatic pressure is available, the starter control valve does not open. This information is given from the SOV feedback switch via the MAU to the FADEC. The FADEC recognizes that the SCV remaining closed after the open demand is an indication that an unassisted start has been requested. The FADEC recognizes that the SCV remaining closed after the open demand is an indication that an unassisted start has been requested. The FADEC automatically commands ignition and fuel flow at 6.9% N2 or after 15 seconds if 6.9% N2 is not yet reached. The FADEC will schedule fuel flow to accelerate the engine and turn off ignition as idle speed is reached. The FADEC start protection logic provides automatic hot, hung, and no-light start protection with the aircraft weight on wheels. Hot and hung start protection is inhibited in the air so that the FADEC cannot prevent an in-flight start. The hot start protection will terminate the start when ITT rises above 815 degrees Celsius during a ground start by closing the fuel metering valve and shutting off ignition. The FADEC will not de-energize the starter driver in this case to allow immediate engine cooling by motoring. To terminate motoring, the stop-run-start switch has to be moved to stop. Engine restart is allowed when ITT is below 120 degrees Celsius. The hung start protection will terminate the ground start when the engine has lit off but N2 dot, the N2 rate in percent N2 per second, goes nearly to zero before idle is reached, by closing the fuel metering valve and shutting off ignition. The FADEC will not declare a hung start if light off has not been detected, because the engine might be motored. In flight, the FADEC will not provide hung start protection. The no light off protection will, like the other protections, terminate start on ground only. If no light off is detected, the FADEC will terminate the start by closing the fuel metering valve, shutting off ignition, and de-energizing the starter driver. The engine can be dry motored either for maintenance reasons or automatically if the residual internal turbine temperature before engine start is above 120 degrees Celsius. To perform a dry motoring, the ignition switch has to be selected to off. The thrust lever has to be in idle position. If the start-stop switch is selected to start and released to run with electrical power and pneumatic system available, the engine will dry motor until the start-stop switch is selected to stop. The first dry motoring is limited to 90 seconds, with a cooling period of 5 minutes afterwards. And then another 4 30-second dry motorings can be performed with a 5-minute cool down in between. Consecutive starts and motoring are limited by air turbine starter oil temperature. The starter is capable of making 3 consecutive starts of maximum 60 seconds each, with a 10-second cool down between the starts, followed by a 5-minute cool down. The starter is also capable of motoring the engine for 90 seconds, followed by a 5-minute cool down, followed by a 30-second motoring and a 5-minute cool down. The ATS may be re-engaged at any speed up to the starter cutout speed of approximately 50% N2. The FADEC will prevent re-engagement of the starter above 50% N2. If during ground starts no light off is indicated within 5 seconds, or during in-flight starts no light off is indicated within 30 seconds, the start procedure should be discontinued. The start can be manually interrupted for any unusual condition by selecting the stop-run-start switch to stop. The failure should be investigated before the next start. Fuel shutoff to shut down the engine is commanded by moving the stop-run-start selector switch to stop. If stop is commanded on ground, the FADEC shuts down the engine by commanding a test of the overspeed system. This test will be delayed by at least 0.2 seconds to allow the aircraft electrical system to transfer electrical loads from engine-supplied power to aircraft-supplied power. If stop is commanded in flight, the metering valve is closed and a momentary FADEC hardware reset is commanded. The FADEC will only override the stop switch request when the thrust lever is above idle to prevent inadvertent engine shutdown. The stop switch signal is routed directly to FADEC channels A and B, and also through the MAU to the FADEC. If all stop signals have failed, the engine has to be shut down by pulling the fire handle. The FADEC will shut down the engine automatically under the following conditions: loss of 2 fuel metering valve feedback signals, large feedback soft fault, loss of 4 in-2 signals, or 3 overspeed trips within 30 seconds. System failures are indicated on the ICUS. The Engine 1-2 starter valve open message indicates that the SCV is not closed when the engine is running. Engine 1-2 fail indicates that an uncommanded engine shutdown has occurred. If the thrust lever is not set to idle during an engine start, the Engine 1-2 TLA not idle message will illuminate. This indicates that the thrust lever should be moved to idle. This message will also illuminate if an engine shutdown is commanded by the stop run start switch when the thrust lever is not at idle position. Further information for troubleshooting is available on the CMC pages.